Hello everyone, and welcome back to the channel. Today we are going to understand one of the most important concepts in digital signal processing, the sampling theorem. This idea is the foundation of how continuous real-world signals become digital signals that computers can process. By the end of this video, you will clearly understand what sampling is, what the Nyquist rate means, and what causes aliasing. Let's get started. In the real world, most signals are continuous. For example, your voice, sound waves in the air, temperature over time, radio waves. These signals change smoothly and continuously over time. We call them continuous time signals. Mathematically, they exist at every instant in time. But here is the problem. Computers cannot process continuous signals directly. They only understand digital data, zeros and ones. So we need a way to convert continuous signals into digital form. That process is called sampling. Sampling means measuring a continuous signal at regular time intervals. Instead of capturing every moment, we take snapshots of the signal. Each snapshot is called a sample. So instead of a smooth curve, we get a sequence of discrete points. These samples can then be stored, processed, and transmitted digitally. This is the first step in converting analog signals into digital signals. In real electronic systems, sampling is performed using an analog-to-digital converter, or ADC. The ADC takes an input signal, measures its amplitude at fixed time intervals, and converts each value into a digital number. This process is controlled by a clock signal. The clock determines how often we take samples per second. This rate is called the sampling frequency, often written as Fs. The higher the sampling frequency, the more accurate our digital representation becomes. But sampling too slowly can create serious problems. And that brings us to the most important concept in this video, the Nyquist rate. The Nyquist rate tells us the minimum sampling frequency needed to correctly reconstruct a signal. It states that the sampling frequency must be at least twice the highest frequency present in the signal. Mathematically, Fs is greater than or equal to 2 times Fmax, where Fs is the sampling frequency. Fmax is the maximum frequency of the signal. If we follow this rule, we can perfectly reconstruct the original signal from its samples. This is the core idea of the sampling theorem. If we sample fast enough, the original signal can be fully recovered. This means no information is lost during sampling. The reconstructed signal will look exactly like the original continuous waveform. This is extremely important in systems like audio recording, mobile communication, Wi-Fi, radar systems. All of these rely on correct sampling. Now, let's talk about what happens when we break the Nyquist rule. If the sampling frequency is too low, something called undersampling occurs. In this case, we do not take enough samples to represent the signal accurately. As a result, different signals can start to look identical after sampling. This leads to a serious problem called aliasing. Aliasing is a distortion effect that happens when a signal is sampled below the Nyquist rate. When aliasing occurs, high-frequency signals appear as lower-frequency signals after reconstruction. In simple terms, the signal lies about its true frequency. For example, a fast-rotating wheel may appear to rotate slowly or even backward in a video due to aliasing effects. This is not real motion, it is an illusion caused by insufficient sampling. To understand aliasing, imagine trying to draw a fast-moving wave using too few points. Instead of capturing the real shape, you connect incorrect points. The result is a completely wrong waveform. This is why aliasing is considered a serious error in digital signal processing. Once aliasing occurs, the original signal cannot be perfectly recovered. That is why proper sampling is critical. There are two main ways to avoid aliasing. First, increase the sampling frequency so that it satisfies the Nyquist condition. Second, use an anti-aliasing filter before sampling. This filter removes high-frequency components that could cause aliasing. By combining proper filtering and correct sampling rate, we ensure accurate digital representation of signals. The sampling theorem is used everywhere in modern technology. In audio systems, it determines how often sound is recorded per second. In mobile phones, it ensures voice and data are transmitted clearly. In Wi-Fi and 5G systems, it helps convert analog radio signals into digital data. In medical devices, it allows accurate measurement of heart signals like ECG. Without the sampling theorem, modern digital communication would not be possible. Let's quickly summarize what we learned today. A continuous time signal is a real-world signal that changes smoothly over time. Sampling converts this signal into discrete values at fixed intervals. The Nyquist rate tells us the minimum sampling frequency needed to avoid information loss. If we sample too slowly, aliasing occurs, which distorts the signal. By following the sampling theorem, we can perfectly reconstruct the original signal. In the next video, we will go deeper into quantization and ADC, how continuous values become binary numbers. You will learn how amplitude is converted into digital bits and what quantization noise really means. Thanks for watching. If you found this video helpful, please like the video, subscribe to the channel, and turn on notifications so you don't miss the next video in this DSP series. See you in the next one.